Hello. So now we'll do an example onto the free expansion. We are having this insulated chamber. This is an insulated chamber, whole chamber. In this insulated chamber, there is a partition. This partition is dividing the two sides. Here we are having N2 number of moles at T2 temperature monatomic gas. And here the temperature is T1 and number of moles are N1 and it is also a monatomic gas. Okay. The volume of this chamber I am assuming as V1 and the volume of this chamber I am assuming as V2. So total volume of this insulated container is V1 plus V2. Okay. So in this case, if I remove this divider, and I'm not moving it, I'm removing it. If I remove this divider, what will happen? When this divider is there, these molecules, these atoms are moving in their respective chambers, only in this respective chambers. Okay. Here also, it is moving in their respective chambers. So when I remove this, after removing, these atoms will move on to this side and these atoms will move on to this side. So after removing this divider, the N1 number of mole will occupy the V1 plus V2 volume. Similarly, the N2 number of moles here, which was in this chamber, they will occupy the V1 plus V2 volume, meaning they will occupy the whole volume and they will also occupy the whole volume. So after removing it, we'll have the combined chamber, and in the combined chamber, there will be N1 plus N2 number of moles. The temperature will be something T, it will change, and total volume will become V1 plus V2. Okay, and obviously the gas will remain monatomic because both were monatomic. Both the gases were monatomic, so the gas will remain monatomic. Okay, so let's solve this problem. In this case, if you are seeing, since we are removing the chamber, the volume is getting changed for this gas as well as this gas, but not by moving the piston, but by removing it. So work done by gas, and I'm talking about gas 1 as well as gas 2. Will be 0. So there will be no work done by the gas. Either this N1 number of mole or this N2 number of moles, they will not be doing any work there. Okay. So the work done by gaseous molecules will be 0. Expansion will be happening but without doing any work. Okay. And now if you see, this chamber is completely insulated. This chamber is insulated chamber. Since this chamber is insulated, there will be no heat transfer between the chamber and surrounding. So dQ will be 0. During this process, there will be no heat which will be coming from outside or which will be going from inside. Okay. So the dQ is 0. So if I apply the first law of thermodynamics, first law of thermodynamics. If I apply the first law of thermodynamics for the combined chamber, then I can say which is dQ is du plus dW gas. And since I'm applying it for the whole chamber, I have to write it for 2. So dQ for 1 plus dQ for 2 is equals to du for 1 gas 1 plus du for gas 2 plus dWg for gas 1 plus dWg for gas 2. So I applied the first law of thermodynamics for both the gases. Okay. So dQ is 0. This value is 0 because both the chambers are insulated. Similarly, this value is also 0. This value is also 0 because the volume change is happening not because of movement of piston but because of removing the piston. This is the free expansion. So because of that, we'll get du1 plus du2 is 0. Or we can say u initial for 1, u final for 1 minus u initial for 1 plus u final for 2 minus u initial for 2 is 0. This is the change in internal energy for N1 moles and this is the change in internal energy for N2 mole while moving from this point to this point. Or we can say U final for 1 plus U final for 2 is equals to U initial for 1 plus U initial for 2. Okay. So the final internal energy of 1 and 2 will be similar to the initial internal energy for 1 and 2. So we'll write those values. And internal energy, we have a formula for that. So let's write the final internal energy for 1, this. So number of moles are N1. The specific heat, I'll write that as CV1 into T, because the final temperature of the gas is going to be T, because when there will be a thermal equilibrium, all the gas will be having the same temperature, plus 2 N2 CV2, specific heat for 2 into T, is equals to initial internal energy, that was N1 CV1, the temperature was T1. Initial internal energy for 1 is corresponding to the temperature T1, plus N2 CV2 T2. Okay, so we want to calculate the temperature, final temperature. So we'll have a formula, final temperature will be equals to N1 CV1 T1 plus N2 CV2 T2 divided by N1 CV1 plus N2 CV2. This becomes like a general formula. Okay, general formula. Now let's put the value for CV1 and CV2. Now in this case, if you see, both the gases are monatomic. So CV1 as well as CV2 both will be same, and that will be equals to F by 2 times of R, and the value of F for both will be 3. So it will be equals to 3 by 2 times of R. Let's put the value. If we put the value, we'll have T is equals to CV1 will put F by 2R, CV2 will put F by 2R, and below also will put F by 2R. So we can take everything common, and we'll have N1 T1 plus N2 T2. They will cancel out. CV1 CV2 cancel out. Divide by N1 plus N2. Okay. So this becomes our final temperature. By putting the values of N1 and N2, we can get the final temperature. Let's, for an example, if the N1 and N2 are same, if N1 and N2 are same, in that case, this final temperature T will be equals to T1 plus T2 by 2. So this is a general case, meaning if on both the sides, if they are not monatomic, one side it is monatomic or other side it is diatomic, we can put the values of CV1 and CV2 here, and we can get the final temperature corresponding to that. Since in this question we have taken both the gases to be monatomic, so these CV1 and CV2 will be same, so they will cancel out. If they will cancel out, this is the formula we get. And if the ratio, if the number of moles on both the sides is also same, which is not in the case, the temperature will be equals to the average of 2. Okay, so that's how we solve the free expansion questions. Thank you.